after 4 years. So I was, of course, a postdoc of the Petty's group, right, for 2 years here, and it was a pleasure to be here, and it's great to be back, especially thanks to Petty and Marci to arrange also on an unusual seminar day so that we can have also some discuss. I can discuss questions with them and then with Tamas afternoon and so on. So today what I'm going to talk about is priority-based matching problems, and we are going to look at only one-to-one problems, by the way, so that because just even now I say we cannot immediately get generalized to many-to-one or so on, or it depends on what type of structure that we have in the problems. So we are focusing in this project one-to-one problems, and then we are looking at limited farsightedness. What do I mean is that actually we are going to look at the mechanisms, matching mechanisms, specifically like the DA, TTC, the classical top trading cycle, deferred acceptance, from farsighted point of view. So we are looking at the classical concept of stability. In the literature, we have myopic or perfectly farsighted cases, based on actually going back to Harshani's critique, right? These definitions which I will formally define. So here what we are going to do is that like an intermediate degree of farsightedness that is actually observed in some experiments as well. And we are going to look at especially the properties of the mechanisms because of this trade-off between the efficiency and stability that we have essentially in the classical model, right? Whether we can say something about those mechanisms under farsightedness. And that's a joint work with Mauleon and Vincent Vannetelbosch from UCLouvain in Belgium. So what I'm going to do is classical overview and then introduce the just formal model of matching problems, priority-based problems. Then for these problems, I'm going to define the solution concept that we are interested in the case of farsightedness, right? Normally, of course, we have the stability notions, and then if we go back even to von Neumann and Morgenstern, right, the solution they suggested in the book in the book was the stable set, so that a set of outcomes with some properties. So we are going to adapt that notion of stable set to horizon K, so that this farsightedness K step further we are going to look right instead of perfect farsightedness. And then in that case, we are going to look at what type of matchings are actually there, or what happens to the mechanisms that we are normally using in the problems that we are tackling in such problems. A side result, interesting results, I'm going to obtain when agents own the object like the Shapley-Scarf model in some sense, okay, the housing market. So it's just relevant and interesting result in that case. And I will try to go on to the matching with couples where normally even we have these negative results also. So I will try to get some results on show you some results on matching with couples model if we think of farsightedness, especially limited farsightedness. And of course, actually we have some more results, but of course I'm not going to go just put all the definitions or adapt definitions and then obtain some results, but try to focus on and then emphasize what we are actually trying to do here with these horizon case situations. So it's going to be classical concept that all of we know actually here in today, but let me just do for the sake of presentation now. So when we think of the priority-based matching problems, we have objects like the school seats, like the college admission problems in Hungary or in Turkey, like in lots of countries, that we are going to allocate them based on some preferences of the agents, that their options that they would like to be part of, and then on the other side, we have the priorities of those objects, and then those priorities, if it's a centralized exam, of course, that comes from a test score, and then you have this GPA score from the university, then you get some rank at the university, right? So this is the priorities, and they tend to reflect some public policy or the desire of the desideratum of the policymaker in these centralized mechanisms, right? And then we assign them through some mechanisms by means of the priorities and then the preferences in the market. And the main solution that we are looking at is this. Of course, the outcomes are the matchings, right? We try to match these agents with two objects. And the main concept is the stability, so that if we just go back to main, like the class for general, not just for matching, essentially what we are saying is that there shouldn't be an outcome there, and then shouldn't be some subset of agents that could be strict derivative of by not hurting others at the same time the market, right? So when we look at the priority-based matching models, the stability concept, of course, has been studied from two approaches actually. The fully myopic agents, meaning that they don't have any anticipation of the reaction of other agents to their actions. So it is not best reply or anything. Let me just already start. It is essentially just looking at some binary relation, like dominance relation, whether we can be strictly better off or not, like comparing two outcomes in some sense. When they are fully myopic, what we mean is that I'm not going to be able to anticipate others' actions to my reactions to my action. But it doesn't mean that these actions are actually or reactions are going to be done. But just looking at what can be done against my action, right? To evaluate, in some sense, a property to evaluate my outcome. And on the other side, of course, these myopic agents, the stability concepts, again, if we think about this von Neumann-Morgenstern to the solution concept, right? Harshani, that dominance relation that we can define this binary relation actually to compare two outcomes given a market, so that Harshani's critique was that the direct dominance actually do not see all or that explain all possible outcomes, so that there should be an indirect dominance. So we could be able to see this pattern of like a sequence of outcomes that may actually lead to another point in this possible set of possible outcomes that actually can be dominated by through this binary relation actually. And then if we, based on this critics of Harshani, actually this farsightedness has been adapted in coalition formation and matching problems, and then in the case of perfectly farsighted, but it tries to say that the agents are able to anticipate, fully anticipate the reactions of other agents to their actions. Again, it is not actually, it sounds like, of course, this higher belief and so on, it's a cognitive thing if we think of that, but it is not exactly like the higher beliefs, because it's not best reply, or like stability doesn't say anything about this higher belief orders, right? Because it doesn't say anything about the best reply per se, like the initial. It's more like a property if you want to see it. I mean, from my point of view, farsightedness, especially in the matching problems and such problems, or even for the cooperative games, it is more like a property of the stability, right? Like how I can define this, how can I evaluate outcomes through these possible reactions to my actions. So these two have been studied in the literature, even for the priority problems, the priority-based matching problems. Included, we have a paper on the school choice. But then what we see is that, of course, these two are in some sense extremes, right? When we are agents with fully myopics and then perfectly farsighted. But when we look at some experimental results, there is a limited farsightedness of the agents in the market. So there are some. There's Tataria-Kova and Trimeron paper, for instance, on network formation. So it is actually a generalization of the structure of the market as well, right? What they observe is that the markets, the subjects are either actually myopic or they have some farsightedness, so they are able to evaluate these sequences up to some point. So there's an intermediate degree of farsightedness in the markets, actually. They don't need to be fully farsighted. So this is one of the questions that we were interested in, whether that is interesting also for the priority-based matching problems, especially if it may be not straightforward to see this, but that we can actually observe some farsighted behavior as well. For instance, in the priority-based matching models, for instance, this French teacher assignment problem, like if you apply, teachers actually get some points to be on the priority list if they work at, for instance, a school with the disadvantaged children and so on. And of course, there are some movements of this, because if they want to move to another school after some years, they know that they might do actually change at these schools in order to reach a better school. So in some sense, they do this cognitive thinking towards like the farsighted behavior in this market in order to reach their actually desired school. So we see this such, and actually now there are recent working papers, Antonio Nicolo, Pietro Salmolo, and one co-author as well, I'm sorry, like that, because it's recorded now, from Padova, and then they do this dynamic one-sided matching problems. So essentially, agents enter to the market at some point, and they can enter to the market. Some agents enter to the market in a different time point, but this dynamic approach, this dynamic market is not blocked dynamically. So the blocking is still based on the static or given time. So in some sense, they are looking at the end matching. According to them, the Italian kidney exchange has this problem, this dynamic problem with this layer change. So there is this farsighted behavior in this dynamic market literature now as well. So these are the main idea that we have behind this paper. Since we have this fully and myopic and perfectly farsighted agents, what happens if they have intermediate degree of farsightedness? And of course, what we are going to do is to study the mechanisms. Like we would like to see what happens to mechanisms, because we have especially like well-known mechanisms in these problems, right? We have the Galen-Shapiro deferred acceptance and the Gale's TTC that we can apply in these markets, and then of course we have the immediate acceptance. So these have, of course, some properties, because these mechanisms select some matching after implementing in the market, right? And based on given any problem, what they do is to pick a matching, right? And then these mechanisms have some properties. We know that both mechanisms are statically proof, meaning that there is no, it's weakly dominant for them to introduce their true preferences. So misrepresenting your preferences, lying is not better off, makes you better off in this mechanism. So manipulation is not possible for one side, of course. And we have this famous trade-off in some sense between efficiency and stability, right? So we know that uptrending type cycle mechanism is Pareto efficient, while DA may say deferred acceptance may select inefficient matchings. On the other side, DA is always going to return a stable matching, while TTC might select an unstable matching. So why I'm insisting on these properties, which I'm going to fully discuss, because we would like to see what happens if we are thinking about farsightedness. So when we look at actually this, of course, efficiency in the case of farsightedness is not going to change, right? How efficient is the matching. But what we can look at is that there's stability. So that's why we are focusing on the concept of course, the stable set as well. And what we know in the myopic case is that actually the TTC is minimally unstable based on some evaluation methods they considered in Doğan and Evler's paper in AIJ Micro, that TTC is the minimally unstable among the Pareto efficient and strategic proof mechanisms. And then we don't have these three properties together, right? And then more importantly, whether we can merge in the context of farsightedness, the stability and efficiency. That is our question in mind, to see what happens to these mechanisms. Because we have seen in a recent paper, and finally got accepted in the games actually, with Anna and Vincent, we looked at the school choice problems. Finally accepted in the sense that just recently accepted, I wanted to say, not like it should have been accepted. So what we look at is that actually these mechanisms where the agents can coordinate together. So we allow to this farsightedness, this actually cognitive approach in a coalitional context, right? So that we allow two agents to move towards an outcome or think towards an outcome as a coalition. So it differs from this paper in that context, because it means that a coordination is needed. If we are talking about the coalitions of agents can do this thinking together. But in that case, we see that TTC mechanism becomes farsightedly stable, so that the matching that it returns actually is stable in the sense that farsighted, and we are talking about perfect farsightedness, while the deferred acceptance becomes destabilizing in some sense, okay? So this was interesting for us, but of course, this farsightedness should be taught for movements by agent actually, instead of coordination, yeah.
Do you have any idea when, how many steps when it becomes?
In this paper, no, but this one is not like a scale, no, but here we have like some, I'm not going to talk about that actually.
Yeah.
But yes, like the agent becomes unstable after
Depends on
the agents and so on, but that No, actually, no, it's up to 2, the A is stable. After 2, you lose the 2 to 3, K3 makes it difficult. And it depends on the number of agents in the cycle. So you like if you look at TTC type of situations, look at the number of agents, and then it is really important because that our proof is also a bit exhaustive on the TTC cycles. So that number of agents in the largest cycle is very important, and then we can see actually where that K is playing a role. And at the end here, what we show is actually that there is some lower bound like that for K to make TTC farsighted, but DA is farsighted stable for small Ks actually, like, but after 2 it becomes really. Oh. So based on this result also, especially for the school choice, our question is that in the one-to-one cases now, because we see that we cannot generalize too many to one, can we stabilize the matching obtained from the TTC mechanism under the limited farsightedness? Because we expect that DA is not going to be, I mean, I'm also proposing like that because that's going to be the situation, like TTC is going to be the nice one in some sort. And if we can do that, how much farsightedness we need for the TTC? And to do so, I'm going to introduce you the horizon K stable set. So that this is going to be my point. And then we are going to see that once they are sufficiently farsighted, it's going to become stable farsighted, stable TTC, but the A may not be. And hence actually the Boston mechanism neither. And moreover, if we think of like directly like as a mechanism, right? So that the single matching set that consists of only this single matching obtained from TTC, so that's why the TTC matching, right, would be a horizon K stable set if this the degree of farsightedness K is actually 3 times the number of agents in the largest cycle of the top trading cycle. Because what happens is that essentially is that agents in these cycles towards looking to TTC matching. They first get assigned to the object that they have the highest priority. Then they change their priorities between themselves and then drop the position actually at the object so that the other agents can get those objects to get better off. And then towards looking at their favorite at TTC matching, they can go to them so that they make themselves in some sense a bit worse off in between to reach to TTC matching. And since it is farsightedness, you don't ask like Harshan need to be strictly better off each step. You just really look at the case step further direct. So this is the difference. And when they own the object, this is I think an interesting result as well. When we look at the housing markets of the shapeless car, so if each agent owns an object, the priority of the objects are just going to be the owner has the priority and that's it at the objects. Okay, if we think of that problem, then actually TTC becomes the unique horizon K from a Morgenstern stable set. So because normally it doesn't need to be the unique one, but if the owners of the objects have the priority at the objects that they own, then it becomes the unique stable set. So just a quick formality here, not formula, although all of us know this. A one-to-one priority-based matching problem is just consists of a set of agents, right? We have some agents, and on the other side we have objects, say schools. Then we have the preference profile of agents, strict preferences over schools or objects as usual. On the other side we have the strict priority structure of the objects over the agents. Nothing is out of the context here. And then rank, of course, now I'm just going to use this. So the rank of an agent is just denoted by FSI, so that I is ranked at some point at school S, and then this number is denoted by FSI. And then, of course, if you have a higher priority, then this rank is smaller than the agent J if you have a higher priority at object S. And then we will look at this agents, the set of agents, right, at a given object S. All agents, the set F plus, F superscript F plus is just going to be the set of agents J that have higher priority than agent I at school S. that we are going to use it like it's in some sense like upper counter, no? That we are going to use for in the proof when we construct a path towards a match. Here I define the outcome of like the problem matching, of course, but a bit different since I'm using these pairs actually a lot to reach to the through any horizon K paths. So imagine mu is just a collection of pairs of agent with objects, right? The objects are assigned to a student, or students are not matched to anyone, but each object at most assigned to one student or like an agent. So this essentially is just one-to-one matching with priority-based matchings, right? Nothing different here, nothing surprising here. And we say that a matching is Pareto dominated mu is Pareto dominated by another matching mu prime if all agents are as good as if all agents are at least as good as under matching mu prime than matching mu, right? And some should be strictly better off under mu prime compared to the mu, and then the matching mu prime is gonna Pareto dominate matching mu. And of course, if a matching is not dominated, Pareto dominated by another matching, then it's gonna be a Pareto efficient matching. And this is just for the properties, of course, that we are gonna check for the farsightedness, and then a matching mu is stable if it satisfies the classical conditions, right? We can write it like this as well. It has to satisfy individual rationality. So first, right? Meaning that for all agents, the matching mu should assign acceptable to them, so that they should be at least as good as being alone up or being unmatched. And then if a student or agent I prefers an object S more than their assignment mu I under the matching mu, then actually at this matching to that object someone should have been assigned, otherwise it would be wasteful, right? Because it would be empty space. So this is the non-wastefulness for a matching, a property of non-wastefulness. And finally, it could be the case that given a matching mu, an agent is assigned to mu I, and then a school object mu I, at the same time, agent J is assigned to an object S that is mu J. So if an agent I prefers mu J more than her own assignment, she has an enemy towards that object S. But then, if the other agent J has a higher priority, of course, at school S than I, then of course this envy is not justified, right? Because someone is assigned to that object and then they already have a higher priority. So if we satisfy these three conditions, imaging satisfies these three conditions, then it is stable. So until now, nothing is surprising, nothing is actually new, right? And what we are gonna do again, based on these properties, I would like to check this important conditions, right? The properties, because we know that TTC is part efficient, while DA is not, I mean may not. And on the other side, DA is stable, while TTC may select unstable matching. And we are gonna try my main question here again as I finish the model going towards the our concepts now. I just wanna recall that we would like to see whether we can stabilize these matchings or mechanisms in the farsightedness, in the case of farsightedness, and then how much actually farsightedness is related to the Tamás question, actually, no? How much farsightedness do we need from the agents in order to reach this possibility, this concept? And these questions, of course, asks for adaptation of well-known concept, like the stable set, and then we are going to introduce to horizon K von Neumann-Morgan stable sets. So, in order to define stable sets, actually, I should, since it is now with farsightedness, I need some notations in order to identify actually my paths, because I will have sequence of matchings, right? So I would like to reach from one matching to another, although I'm not going to take into account the relationship or like dominance. I'm not going to check that, but I'm going to look at these possible reactions. So I need to be able to identify these sequences. So let me just give some preliminary notation here to define and use my to introduce my notion. So given a matching mu, where an agent I is assigned to an object, we can write a matching mu prime as mu minus is, meaning that actually the agent I drops its object S. So there is actually under the matching mu, they are assigned to each other, but agent I, of course, is the owner of the object, and objects actually do not have any preferences or anything, right? They have priorities, of course, but they are public goods in some sense in most of the cases, right? So here, yet, I don't say anything about its owner, but normally we can at least denote another matching mu prime that we can reach from mu by determining the partnership between I and S. So I drops S from her matching, right? Be assigned. On the other hand, we can reach to another matching mu prime where this agent I and an object S are not matched to each other, assigned to each other under mu. I can match them, right? I can form a matching between them, assignment between them to reach this matching mu prime. But of course, if they are matched to another, so if an agent were already matched to another object, then this object should be single, actually unmatched under mu prime, and then also I should break the partnership or the assignment if an object is owned by someone else under matching mu. And of course, in order to do that, I should actually be careful with the priorities, but it's not that point, but yet it's just for this notation of what do I mean by mu minus and then mu plus essentially for this new partnerships. So based on this notation, I can identify a horizon K improving paths. So we are going to try to go from one matching to another in K steps, right? So it's going to be a finite sequence of different matchings, right? Starting from a matching mu, and it's going to end at matching mu prime after and capital L steps, okay? And these steps, this L steps actually is going to be a horizon K improving path such that either an agent at a given step, lowercase n, can actually deter her partnership with an object S, such that she should compare as an agent I, she should compare whether she gets strictly better off or not after K steps compared to the current place where they are, a step where they are. So what I'm looking at is actually K step further, and of course this minimum LK, L plus K and capital L is due to the fact that I could be looking K step further, but of course it's a sequence, so it could be N matching already, so that I don't have to go further. I cannot go more than actually this capital L, so that's why I have this minimum between these two options. But what it essentially says is that either an agent can break her assignment, get rid of her object, knowing that at the end, K step further, they are going to be strictly better off, or they are going to form a partnership with an object, looking at also the K step further, knowing that as an agent she will be better off, but at the same time, of course, I should identify her, I should look at the object, right? Because if I'm forming this partnership, it means that the agent actually drops her object at that given step L, and then I should break also the partnership the object has at that moment. But of course, in order to break this partnership, in order to form this one, I should be sure that not just the agent is strictly better off, but also that this object S that she will be able to assign that has a higher priority than the owner of object at that given point.
So this is for a real optimist, right? So there is at least one who K step horizon. Okay, there is someone, but maybe many others, maybe all but that one could be girls, right?
Yeah.
Yeah. So,
but also we do not like because we only allow one person to move at each step. Because that's what you're asking, right? I'm not gonna.
yeah, but who is moving next?
Yeah, of course. Okay. who's moving next to
Okay,
them.
so, but.
They also
but-
wanna look at the
but
case step
For
further.
some,
Yeah.
you say for some, it means that, okay, if I have even a small chance, if it's stochastic, but it's not, but there is one, then I will go for that. According to your.
Yes,
It's an improving path, so it's,
yes, but
okay.
in order to identify
I
this,
don't
in order
understand
to identify that, yes.
Okay.
If I have that chance, then I will go to that. Yeah, I can define this improving path exactly. So that I will use this improving path whether I can reach or not, because it doesn't, I'm not trying to also to make myself to reach to that matching, for instance, right, to that outcome, but just compare, I know that I could, if I move, they could move, and then knowing that, looking towards TTC, that would be this moves. And then hence, this is a possible way to reach to that one, right?
But it cannot happen that, okay, at the moment, I see that 3 steps from now, there is one, okay, I will try to reach that because that's better for me. But during that steps, someone just kills that one because this is, another player,
Yeah.
and then I'm losing all. I'm losing that
okay,
one
okay.
for which I was
So, but you just
aiming at,
okay.
but
But
anyway.
you know that, but okay, then yes, like you know that there is a, it's not stochastic, but even if I have a small chance that I could be reached, so yeah, I know that there exists, no, like it could be the case that I can.
Yeah, but
reach
that one could be killed by someone else after me.
But in order to kill that,
I mean, because,
they have to,
okay,
but because
Yeah.
they would make move, right? You mean, but then since
they could take my
Object.
my object, which I would like to get, but yeah, intermediate step, someone.
but if they have a higher priority, then you would already get it, right? You cannot reach to that object.
Okay, go ahead, please. No, just,
No, that's the most important to understand,
Yeah.
so what is, so on these
Just put
panels,
this- yeah.
you might have to make sure that.
I will compare with the case step further. Some other people do some possible movements as well, but I'm just checking that whether I will be able to, I would be able to define this improvement path. So like this move goes to there and so on, and then whether there exists a path that would reach to another matching in case steps.
But it's also important that if this is a step by another person, other agent, then it should be also. An improving path for that other agent, isn't it the case, with the same horizon?
At the same step,
So. I'm doing a change.
Yeah.
I think that within k steps,
Mhm.
I can get a better solution.
Yeah.
Now, these k steps will depend on other agents'
Mhm.
decisions. And do I understand correctly that these other steps, which are the decisions of other agents, should be also motivated by the same reason? They also should be able to hope for a better
Yeah.
solution
Yeah.
while they are moving
Yeah.
these steps.
Yeah.
And everyone has the same horizon
Yeah.
K,
yeah,
so everyone
true.
should move in such a way that in the end, after at most k steps, they see a matching that is.
But for instance, when I start from here at the end, like the other one is not looking a step further from there, but wherever she is, no, like when if I get someone else's object, they are gonna looking forward to that from that step to K further, they can still go somewhere, right?
Yeah, so if I am taking an object of
Yeah.
someone else, then this agent who is losing that object.
Yeah.
Can be worse off,
Yes, at that moment, but then
but
because it.
at that
agent,
moment,
but
no, but.
no, but then I don't look at all the agents at a given step, right? If I just make myself better at K step further, it's about me.
Yeah.
I don't look at the others, like I don't expect the others to be strictly better off at the end neither. Otherwise, I cannot reach, I think, to the TTC.
And this K is fixed, so
Yeah.
it's not that step 1, step
No.
2, step K, no, just always K.
Yeah. We didn't
So
make it from
you, your glasses are such that you can
Yeah.
see 20 meters, but you cannot see good for 5 meters. I understand that for 50 is far away.
20, yeah.
Yeah, okay, got that.
Yeah, it's exactly, yeah, it's exactly, yeah. Otherwise,
It's not up
it's
to K, but.
no, it's not up to K, it's the K, yeah.
Got that.
So based on that possible path, I can reach different matching, given a matching mu, I can reach to different matchings mu prime by some improving paths, K-step improving paths, right? Then if there is such a matching, then we write it by right arrow of K, so that it means that I can reach to mu prime through mu, and then all the matchings mu prime, the set of matchings mu prime that I can reach from matching mu through horizon K, improving paths are going to be phi K mu, right? Because I'm going to use this notation to define the stable set, of course. So these are the set of matchings I can reach from a given matching mu. And based on this, now I can adapt the notion of fundamental Morgenstern stable set. So in the myopic case, we have this internal and external stability, right? That a set of matchings should satisfy even in the matching context. In general, of course, in abstract games and so on also, it's the same idea. So how we can define in the horizon K situation? So we look at the set of matchings and say that there's a horizon K stable set if it satisfies internal stability and external stability. So internal stability says that if given two matchings in the set, I shouldn't be able to reach from one matching to another matching. So it's like the binary relation if we think of the general concept of the fundamental Morgenstern stable set, that I shouldn't be able to dominate, or the binary relation domination between them. So in this case, it means that I shouldn't be able to any matching mu prime in the set through horizon K improving path from matching mu. And external stability then will say that I should be able to reach a matching inside, some matching inside the set from from any matching outside the set, I should be able to reach some matching in the set. So if matching mu is not in the set V, then I should be able to reach to some matching from mu through horizon K improving path to set V. That's why this intersection should be non-empty, right? So I can reach something in the V. So if these two conditions are satisfied, then we have the horizon K stable set. In the matching problems, in the context of matchings, in the myopic situation, from A-lars, we know that it is actually unique, and then it has actually a nice lattice structure, it's distributive lattice, and so on. And in the perfectly farsighted cases, we know that one-to-one stable marriage problem, so that with the preferences, we know that singletons of stable matchings are a set, the singleton set that consists of a stable matching only is a farsighted stable set. So for each stable matching, we have a different, we can define a different farsighted stable set in the stable marriage problem. And in the school choice, when we have the school choice type of problems, many to one, but where we have the coordination between agents, then we can have the perfectly farsighted stable set as well, where the singleton TTC is actually the case, is the farsighted stable set, but it's not the unique in that context, okay? So there can be others as well. And of course, in the case of farsightedness also, there are more than one formula Morgenstern, but in the myopic case, there is only one unique stable set. And this is maybe more relevant to what you were suggesting in myopic farsightedness, so that when this society is mixed, so that there are some agents myopic and there are farsighted, but they are fully farsighted, so that they can check that K to the perfect farsightedness level. So in that case, they also Vannetelbosch has a very recent working paper that they check that, and they saw also TTC is actually becomes a myopic farsighted stable set, so it still survives as a farsighted myopic farsighted within a myopic farsighted population section. And here also, of course, that there are only farsighted only one side, okay, in their problem. So this, like in the school choice mechanisms and so on. So the so what we do here is that then look at in the limited farsighted cases, and what I need is for our main result is actually to look at the cycles of the TTC. So what we need is a number that has the maximum number of agents in order to identify the limit of level of farsightedness that we need is actually based on the number of agents in the TTC cycle. So if you look at the cycles in the TTC, normal TTC mechanism, right? And then each round of TTC, that could be more than one cycle. So if it is the first step, it's the maximum number of agents, and the up to K bar step, right? There is like largest cycle. So let's fix that one, gamma, right? Because this is useful to us. We show that for any given one-to-one priority-based matching mechanisms, the TTC matching obtained from the TTC mechanism is actually, as a singleton set, is a horizon K stable set, for K being 3 times the largest number of agents in the, the largest number of agents in the, largest number doesn't make sense. The number of agents in the largest cycle during the TTC mechanism, that's gamma, right? Because I looked at the cycles and then one has the biggest number, the largest number of agents. So that one, 3 times that minus 1, so that I have a lower bound. I need this much farsightedness essentially in order to stabilize the TTC. And it comes from more or less this idea. So first, looking towards the TTC, the agents in the cycles, because we essentially look at this possible cycle formation and then we try to reach to their TTC, right? We have to have to form a horizon in K improving path. So they look at towards TTC. So they first we can construct. The key point is that we can construct an improving path so that the objects that has the like we look at the agents in the cycle and then we first let them to be assigned to the objects where they have the highest priority because they can be matched to that because they have the highest priority. So looking towards the TTC, they can make themselves worse off. So drop it, and the other agents made clear even if they don't have the capacity to reach them through priorities, they can take it because they are dropped by the highest priority agent. So then this highest priority, the agent who had the highest priority can go towards to her TTC machine because we are doing this for agents in the TTC cycles. I'm going to provide an example. Yeah. Okay.
So how many? What is the maximum steps? Because this really looks a long horizon, right? So because in a TTC, in each step,
for instance,
you allocate at least first you start with 2 and then at most 1 each time. So
I mean, it's the largest
number in terms of number of agents.
If I have largest cycle has only 2 agents, it would be 5. I would need at least 5 steps further. But if I have a larger cycles, of course, it's going to be like
2 minus. No, that's fine.
Yeah.
But of course, that's for the TTC. It doesn't make 5.
Sorry?
It doesn't make 5 steps because one cycle length, maximum cycle length is 2.
Yeah, like if I have a So it's indeed, but if I have a maximum cycle of 20 people, 20 agents, then it's going to be 59 steps of farsightedness I will need, yes. Right? So like I have to look at.
Okay.
So because I really go one by one, I just assign first and then drop it. I make myself worse off actually, knowing that I would be able to reach the TTC. I mean, considering that. And then I do it for all agents so that I need to do that for all of them in the largest cycle and
almost practically complete farsightedness, right? So is it this lower bound? Okay,
that's a good actually. That's a good question actually. And then I mean largest cycle, now I don't want to lie, but largest cycle to be 20 and then you have a large amount of agents in the market. So 60 compared to a large market might not be that big perfectly farsightedness then, but
okay, but so in the long run becoming becoming stable, yeah.
Okay, you are saying that no, but now that I never, to be honest, I haven't looked at from that point of view, but indeed from that point of view, it looks like it sounds like.
So in the short run, it doesn't have. Yes, it doesn't have. Probably DA is
after 2, DA maybe that is more interesting. Yes, that is maybe that I can defend this, I mean, not defending, but like I can get from that point of view because it's not defend, I don't have to defend in some sense, no?
Yeah.
It's just a good question and point. That you are making. The A gets unstable very quickly,
Mhm.
let's say, and TTC still survives with this idea, but of course, yes, indeed, in that case, then it's kind of looking to horizon forward, yeah. And in the case of TTC, of course, if we think that since if it's a singleton, internal stability is gonna be satisfied trivially, because there's nothing else in the set. And for external stability, I just need to construct an horizon K improving path from any matching to TTC. That is the only thing I should do. And then that is essentially what we do to give the sketch of the proof in some sense, no? In the paper. Let me give you the example here actually. So if you look at this here, no, like that, 3 agents, 3 objects, just for the sake, I will put the here, I1 points at S1, I2 points at S1, I3 points at S2, S1 points to I3, S2 points to I2, and then S3 points to I2 as well. And then there is the cycle here where S1 points at I3, I3 points, I mean, it's actually not this direction, but I3 points to S2, S2 I2, and I2 S1, right? So this is actually the first step cycle. And then if we match to each other, right, I3 to S2 and then I2 to S1, then I will just end up in the second step, only one agent, right, which are S3 and I1. So if I keep it, and then my gamma here is gonna be, in this case, 2 because I have 2 agents in this one. So what I need is just essentially is to reach to this matching, TTC matching, where I'm gonna assign to this, and then I3 to S2, I2 to S1, which is here actually. So I'm gonna try to reach from any matching in 5 steps to this matching, right? And then try to construct. So I can construct, for instance, starting from this mu naught. But I'm gonna show directly all of it. So we start from here, right? Mu naught is like agent 1 is assigned to school 1, agent 2 is to S2, and then agent 3 to S3. So, but as I said, only one agent is going to move at each step. So looking forward 5 TTC, like 5 steps further, first, if I look at this in the cycle, agents in the cycle, especially, right, I3 and I2, I3 has a highest priority in the school 1, right? I2 is already in the school 2, so she's assigned to that object, but I3 is not assigned. So in the first step of this path, I assign, actually I don't, but like looking forward towards mu5, I3 takes his priority at the school 1 or object 1, since she has a higher priority. So now then I1 loses that position, right, at the school object. Now, since this agent has the highest priority in this object, and then the other agent is kicked, but she would like to reach the TTC matching, knowing that she would like to reach that, she's gonna make herself worse off, so that she's gonna drop her matching here, looking forward, so that she's gonna be alone, since now agent school 1 has an empty slot, right? Agent 2 can go to school 1 instead of going to school 2, which she has a higher, I mean, she prefers more. But normally she couldn't do that because she has actually the first priority at that school. Thanks to I3 looking forward, she can get it. Now, after this, of course, school 2, I2 dropped her position, and now I3 can go towards to her TTC partner object S2 or school S2. Because S2 was left by I2, right? Because she was able to get here. And then at the end, of course, we almost reached to the last point, and since it's by step, one agent can change their, move towards the K step further. Then at the end, I1 is just gonna go to S3 finally to reach the TTC matching. So this is how horizon K improving path is constructed in some sense. And then I can do that for any given match. So I think this was the question, right? I'm here, but I'm looking here, but it's all of the agents are looking at K step further, and then this is like 5 years, so like I know that I can reach there in the 5 steps in some sense. Yeah. So this is how it works. I don't know if it is now more convincing or clear. The idea of the horizon came from impact. To finish maybe like the last 5 minutes, this is a good example because what I can see is that in this example, DA and Boston mechanisms actually return totally different matches. And what we see in this example is that the TTC is the unique horizon K from the Morgenstern stable set in this example. And DA is not actually a part of any horizon K stable set. So why? For given K stable greater than 5, what we see is that actually from DA matching, I can only reach to TTC matching. And then from TTC matching, I cannot reach to DA. So that if I want to DA to be in a set, I cannot have TTC outside of the set, right? Because otherwise I cannot reach to that. And at the same time, I can reach to TTC from DA, so for internal stability, I cannot have this DA to be in the set, right? Because if I reach, there are some matchings actually that I haven't shown, I don't show, but I can reach to DA, that actually is possible to reach from TTC as well. So DA is a subset of a set containing DA. Because of this cannot be a horizon K stable set, no? Because internal stability here and then here the external stability wouldn't be satisfied. And on top of so DA, the important point here is that TTC is farsightedly stable, but DA may not be farsightedly stable. So this is actually kind of a nice property for if you look at this trade-off between efficiency and stability from one point of view, actually we can have something positive for TTC in some sense, right? We still can stabilize it while DA might get destabilized very quickly. And at some point, you might ask whether actually Pareto efficiency is relevant for the farsightedness. And here we see that actually DA of Boston mechanism is here and it's a different matching. And then DA is also here in is Pareto efficient, but we are going to see that TTC is the set consists of that singleton TTC matching is the unique one, so that it's not going to be efficient. Why? Well, because if any other set that containing TTC, right, would violate internal stability because TTC alone should be able to reach any matching from any matching I can reach to that. And at the other side, on the other hand, I should have the DA also in the set, right? Otherwise, it's not going to be externally stable because from DA I can only reach to TTC. But then I know that if the DA is in the set, I know that from the earlier comments that it cannot be in the set. Hence, there is no possibility. So here, TTC is the unique stable horizon K stable set. So maybe to wrap up with these remarks and then the Venn agents have the objects actually just to say. The TTC always Pareto efficient, of course, but may not be stable when the agents are myopic. But we show that with our main result that when they are farsighted, sufficiently farsighted, TTC becomes stable, while DA might not be. And as in the example, and since we show that it is the unique, this singleton set was the unique in this example at least, that we know that actually we show that Boston mechanism also does not, like the Boston matching is not part of any stable set neither, so that it is Pareto efficient as we know. And then one of the questions could be that whether Pareto efficiency is a sufficient condition for the farsightedness and so on. So thanks to this example, also we see that actually Pareto efficiency is not sufficient for achieving farsighted stability, limited farsighted stability. That is what it says essentially. And I'm going to stop here just because I don't want to give the definitions because just I don't have much time neither, no? Zero. So the interesting point then with -1, when we think of the problems when agents own the objects and the priorities of the objects are essentially just to have the owners, right? So in this case, the TTC becomes the unique farsighted, horizon carried farsighted stable set actually. So it is somehow similar to the results of Klaus Klein and Waltz, where they studied farsighted house allocation problems, and they showed that there exists a unique, perfectly farsighted fundamental Morganian stable set. And of course, it coincides with the competitive equilibria, so it is relevant for that. Why it is relevant also? We have first uniqueness, and on the top of it, these papers, the Klaus Klein, like Bettina, Philippe, and so on, and then Kawasaki also studies the same. They allow the coalitional movements. So like coordination between agents are needed on top of the farsightedness. And here, what we have done is that we don't allow the coalition, so the coordination actually. So we don't demand another thing on top of farsighted. And let me stop here. It köszönöm szépen.
Thank you very much. Is there any more questions? Okay, so if you know, then thank you very much for the presentation. And if you have any more questions, then
Yes.
after the presentation. Thank you.